Hello, everyone. I'm going to talk about Python packaging Expressway. I'm Parul Gupta. I'm an engineer working at Python Foundation team at Meta. Today, I'll be talking about how to package your Python code to make it into something that's really useful for other people so that they can use and work off of. But first, who am I? I'm Parul. I am a production engineer at Meta. My main focus is Python third-party libraries and maintaining them with the focus to ensure that these outside packages are imported and are upgraded and are maintainable and just work in our Meta ecosystem really well. Outside of work, I just like to paint and dance. Python packaging. Python packaging is a process of organizing, bundling, and distributing Python code. But why do we really have to package our code? There are various reasons to do so. First is code reuse. Let's say you have this really cool code or some program that does something really fancy and you want to use it across different projects. Packaging is that fundamental part of Python ecosystem that enables you to share your libraries, tools, or application with the community or within your own organization. You can extract out the parts that are reusable and can be used across different Python projects or programs. But it's not just the code reuse. It also helps with collaboration. The other people who want to contribute into your code can easily do so if you package it really well. Then it also allows versioning. With packaging, you can track changes, any breakages that are there that you want to flag to your users, or even if you want to ensure compatibility across different platforms, such as different Python versions or OS architectures or just hardware. And finally, deployment. Packaging also makes it easy to install and run code on different platforms. I personally see this process as preparing a gift. If you want to compare gift wrapping elements with Python packaging, at a very broad level, you can imagine it something like this. The gift itself is the Python modules or the submodules that you want to have. The packaging paper can be seen as package structure on how you set up modules, submodules, or even APIs. The gift tag is the metadata that you define, which can be name, version, or any other tags for your package. The instruction manual on how to use your gift is just the same as the README or any type of documentation files, tutorials, examples, etc. The ribbons or the frills on top of your package, on top of your gift, is seen as anything extras or the optional dependencies that you may want to have. The shipping or the delivery of the package or of the gift is exactly the same as publishing it to the PyPI website for the rest of the world to be used, so that they can use it. And finally, receiving the gift is somewhat equivalent to installing and using it at a different place by your teammates, by your colleagues, by someone on the other side of the world, anyone. Let's get into how do you actually use the Python package. You can install a package with the help of any packaging tool. Here is an example on how pip does it. Let's see what it's doing. It first collects the Plotly. Over here, I'm trying to install Plotly package, and it first gathers dependency information from the Plotly's metadata and resolves to the right set of versions. It then tries to download the Plotly package itself. It then downloads all the dependencies that are not already available. In this case, it's packaging and narwhals. And finally, it installs them in order and then logs that it was successful to do so. But what really happens under the hood? How did we actually get this package? How does it really work? Let's take it from the top. Imagine you have this code containing some of the code files, aka your gift, and it will look something like this. It'll have an init file, it'll have main, it'll have some modules like foo and bar. And your first step is to structure it really properly so that you can reuse it and make sure that it's working. Most of the code that I've seen in open source, they structure it really well. They put it in the source folder. That's one of the common ways to do it. Remember that this code will be used by other people, so you want to make sure that your code is clean and is properly modularized. It helps to ensure that multiple developers can work on it simultaneously. It also helps with scaling. As your project grows, modularization really helps you add new features or components without creating a tangled mess. Then comes testing. If other people are going to use your code, you want to make sure it's well tested. Two of the most popular testing frameworks in Python ecosystem are PyTest and UnitTest. They both provide reliability, flexibility, and are well supported in different ways. It makes sure that your package code is correctly set up, is maintainable, and is ready for distribution. Out of these two, I think UnitTest comes with the Python standard library and doesn't need any installation. However, I do find PyTest to be really easy to get started with. Then comes documentation. It's not just the code itself, but also the supporting documentation that can really make or break the popularity of your package. Always have verbose documentation on how to use or even how to contribute. Create a dedicated website for your package. Then maintain a change log. Any changes that come across different versions or any enhancements that you do that you want to flag to the users, mention them properly in the change log. Examples and tutorials are also a bonus. For any AI-related packages, I really feel that having verbose examples and a lot of examples can really speed up the wrap-ups. And finally, I want to highlight the assumptions and constraints that you may be making for your package and those things that may be needed for your package. It could include the CUDA architectures, the operating system, the Python versions, anything around that. And finally, dependencies. A very basic way to list dependencies for your project is just freezing your environment and copying out all of them in a requirements.txt. Some people also use log files for all the versions to make sure that you can get same exact reproducible environment across different people or across different machines, or even in the deployment. But can we do better? Well, yes, we can do better in terms of dependencies. We can use package managers to manage your dependencies. I'm not here to talk about which of these package managers are better than the other. I know there is a lot to read and you can figure out which works for you, which doesn't work for you. I'm here to focus on how to make your package such that it can be consumed by these packaging tools. All of these more or less respect some sort of standards of built-in packaging, the PEP standards to govern their behavior. Actually, let's digress a bit and talk about these popular PEPs before I go back. I think they're really interesting. For those who don't know what a PEP is short for Python Enhancement Proposal. They're the primary mechanisms for proposing major new features, collecting community inputs, and documenting design discussions for Python. They ensure transparency and help standardize best practices and processes across Python ecosystems. In build and packaging space, there are some key PEPs that I've mentioned over here. 508 is dependency specification for Python software packages. It defines the standardized way to specify dependencies for Python projects. It provides a clear, unambiguous syntax for specifying Python requirements, how to write version constraints or environment markers or extras or optional dependencies. The next two, 517 and 518, they together were a game changer in this industry. They are probably one of the most famous PEPs in packaging space. They modularized Python packaging by making builds more reliable, flexible, and tool agnostic. 517 is a build system independent format for source trees. This basically decouples the project specification from the old setup.py centric approach. The projects can now declare their build dependencies and requirements in a specific section in a configuration file, which is often called by project.toml. 518, on the other hand, is specifying minimal build system requirements for Python projects. It complements the previous one and defines how to declare build dependencies needed to build a Python project. Before this, tools like pip had no standard way of knowing what is really needed by your project for it to be built. It would cause a lot of build failures if the dependencies were missing. And finally, PEP 621, storing project metadata in pyproject.toml. While the previous PEPs were all about the build system itself, this one standardizes how Python projects declare their metadata, such as name, version, author, dependencies, licenses, etc. in pyproject.toml file. You now have a unified location for all of these things, standard fields for all of these values that you want to provide, a tool-agnostic format for the project to be built, be it anything, be it setup tools or poetry, hatch, flut, whatever. There are some things to consider over here. If there is something that I want you to take from this talk today, it is that use pyproject.toml for your project metadata. And I'm here to tell you why. Pyproject.toml is a modern standardized way to define Python project metadata and build requirements as specified in the PEPs that I just mentioned before. There are some features in terms of pros and cons for using setup.py or pyproject.toml. Let's go into them. First is executable code. While setup.py allows for executable Python code, it can be really arbitrary. This flexibility often leads to complex, hard-to-maintain build scripts and makes static analysis really difficult. PyProject, on the other hand, is a static configuration file, making it really easy to parse, validate, and to reason about. This reduces the risk of unexpected behaviors during builds. Then comes standardized build interface. Setup.py, being an arbitrary Python code, doesn't have any standardized interface. However, PyProject makes it really easy to interoperate between different build tools, be it poetry or setup tools or pip, hatch, whatever you want to use. Then comes build dependency management. Both have build dependency management, so I wouldn't say that one is better than other, but I do think that PyProject provides a very clear way of doing it. Then comes being tool agnostic. We already talked about this. PyProject allows you to choose any type of build backend, so you can migrate to newer build systems as and when they come without having to change the interface, either for the users or for the tools. Then comes easy to parse. By moving the configuration out of the executable Python code that the setup.tool provides, PyProject is basically a declarative file, and the projects become way easier to understand and maintain. And finally, community support. I've seen that the adoption of PyProject has been increasing and is more acceptable within the open source community in general. Here is an example of how PyProject looks like. It'll have different sections, for example, project over here, and we'll have these standardized fields like name, version, description, and so on. And this is where it goes into your project structure. It is essentially a top-level file, which is basically the configuration of your entire project. There are more things than just PyProject that I want to focus on over here. The next one is use minimal requirements and add extras dependency. It's basically adding frills and ribbons to your existing project. These are the optional dependencies, or extras is what is called, is another powerful tool in Python packaging that allows for additional non-essential dependencies that users can choose to install or not install based on the features that they're going to use from that project. It helps to keep the core package really lightweight, especially when it comes to these AI packages, which can be really huge and very difficult to interact, and they may interact with different AI models, which require different types of dependencies. They can often be conflicting dependencies, and having optional dependencies defined in your project can be really useful. It also enhances the installation experience for the users. the installation load will be really low. These dependencies you may or may not need. The complex setups you may or may not need then. And it becomes really, the whole life around installing these packages becomes way easier. Here are different ways on how you would add the optional dependencies. You can either add it as part of the project section itself as project.optional dependencies, or you can also add it through some tools like tools.poetry.extras. Both of them are installed in a very similar way. You just do pip install. I mean, I'm using pip. It's just pip install the project name, and in the brackets, you'll have like what type of additional dependencies you want to add. Finally, I want to touch base around virtual environments. Use virtual environments for development, testing, and installation. Isolating project dependencies ensures that you don't cause conflict or interference. It keeps your global Python really clean and stable as you're not installing it system-wide. It produces reproducible development and testing. You can easily recreate the exact environment that your project needs and ensures that your code runs the same way on your machine, your teammate's machine, or even in production. Essentially, you avoid the classic, it works on my machine kind of problem. And all of this makes the development so much better and so much easier. Once you're done with all the specifications and structuring, now the next step is to create a distribution. It's essentially to wrap up all of your GIF together. Creating a distribution for your Python package means preparing it in a format that can be easily shared, installed, and used by others. Let's check how. There are two types of distributions that exist. One is the source dist, which is essentially called the S dist. It is a type of package distribution in Python that contains the original source code of the project with all the necessary files that are needed to build and install the package in any compatible system. Generally, it's in the form of a tarball or a zip. You can build it using Python build --s dist, and it goes in the distribution folder, or the dist folder. The main advantage of doing that is portability. You can build the package on any platform, even if the pre-built wheels are not already available on the PyPI website. You can also inspect the code and modify the code, essentially patch the code, the source code, as you need before installation. The next type is called bdist, or binary distribution. This basically contains the pre-builts, which include the compiled files. They're just ready to install files for Python packaging rather than the original source code. Generally, they're in the form of a wheel or a dot wheel. They're built using Python build --wheel. And again, it goes into the same dist folder. The main advantage of doing that is speed of installation. Installation is much faster because there's literally no build step involved. Users don't need to have any compilers or build tools to install these. They're just readily available. However, they are platform specific, which means that you need to build it for every platform to make it compatible, and that platform could include different Python versions. It could include different CUDA versions. It could include different OS versions, things like that. Okay, now that you have the build, you've already built this distribution, you've wrapped the gift, it's ready for the shipment. And the final step over there is publishing to the PyPI website for the rest of the world to use. The PyPI stands for Python Packaging Index, which is a repository of software for Python programming language. Publishing a package here is literally the final step to make it available. How to do so? Basically, create an account over there. It's very simple. Go step by step. No frills over there. Then upload the dist folder to the PyPI website. It could have. You don't have to directly upload it to the main website. There is a test website available called test.pypi.org. You can first upload it over there. See if all the metadata is included over there. You have all the things. You can download it. If you're satisfied with it, that's when you can upload it on the actual website to make it available to the world. And that's it. That's all there is to publish to PyBeach. Your gift is literally ready to be unwrapped and be consumed by someone else. Basically, it is downloadable and installable to the rest of the world. But there's some things to consider. First is version structure. There is a way to structure your versions and a way to bump it up. You can use a library called bump version to do this, or just do it manually. The only recommendation I have over here is that just be consistent across your versions. Don't keep doing random stuff over there. Then comes software license. License guides users on what they're allowed and specifically what they're not allowed to do with your code. Can they be used for commercial use cases or not? Organizations and companies require a clear license before they can actually use or contribute to the package to avoid any type of legal risk. So make sure that you have chosen the license correctly. And finally, classifiers. Classifiers help with search and understanding of what can be used and cannot be used by the users. Python landscape is huge and complex, often due to cross-platform capabilities that it has. Identifying and mentioning the classifiers in your metadata can be really useful to know what may or may not work for a certain set of users. Here are some of the resources that I used. The one that I would recommend is the PyOpenScience guide. There is also this official packaging guide by Python.org. There is a survey opened for 2025. I would recommend everyone take it if you haven't already. The deadline is in December, but please take it. And the PyPI website, which is pypi.org. And that's all. Thank you. Thank you, everyone.